All right, let's talk about something incredible. This invisible journey that happens literally every time you go online. I mean, think about it. Every single click, every search, every video you stream, it all kicks off this tiny messenger on a pretty epic quest. And it feels instantaneous, right? You click a link, and boom, you're on a new page. But behind that smooth, seamless experience, there's this incredibly complex story unfolding, and it all happens in just a few milliseconds. So what we're going to do is follow one of these little data packets, let's call it our digital hero, on its mission. We're going to trace its entire path all the way from your computer out onto these huge digital highways of the internet to a server that could be thousands of miles away, and then all the way back. Okay, so where does this all start? Well, first things first, our little packet has to know where it's going. You know, just like a letter needs a street address to get delivered, our packet needs a digital one. And that's where the IP address comes in. It's basically the fundamental address system for the entire internet. This IP, or Internet Protocol address, it makes sure our packet knows exactly where to go, and, just as important, it tells the response how to find its way all the way back to you. Now, what's really fascinating is how we used to handle these addresses. Back in the day, the original classful system was, well, simple, but super inefficient. It handed out addresses in these huge rigid blocks. I mean, imagine needing one room but being forced to buy an entire apartment building. That's kind of what it was like. And as the internet started to explode, that level of waste just wasn't going to fly. And this is where the smart solution comes in, CIDR, which stands for Classless Interdomain Routing. They call it classless because it completely got rid of those old rigid Class A, B, and C rules. So instead of being forced to take like 16 million addresses when you only need a couple hundred, CIDR lets network admins be way more flexible. They can allocate exactly what's needed. This was a total game changer for IP allocation, and honestly, it's a huge reason the internet can keep growing. All right, so our packet has its address. It's ready to go, it's leaving your local network and about to hit the wide open internet. But how in the world does it figure out where to go in this massive, complex web? Well, it meets a few key players that are basically the internet's traffic cops. First up is a switch. The switch is all about your local network. Think of it as directing traffic on your neighborhood streets. But once the packet needs to go further, a router steps in. The router is the big one. It's what connects all the different networks together. It looks at that destination IP address and figures out the best, most efficient route for the packet to take across the internet's massive backbone. Okay, now here's where things get really clever. Your computer, my computer, most devices, they have a private IP address, something like 192.168.something. That address is totally private. It's not reachable from the public internet. So, how does it talk to anything? Well, the secret is a little something called Network Address Translation, or NAT. So, think of your home router like a big company's mailroom. Every employee, that's every device on your network, sends out mail, but it all goes out under the company's single public address. When a reply comes back, the mailroom clerk, your router, knows exactly which employee to give it to. It does this by swapping your private IP for its public one on the way out, and then swapping it back on the way in. And here's the real aha moment. This trick, NAT, is pretty much the main reason we haven't totally run out of the old IPv4 addresses. It lets billions of private devices share a much, much smaller pool of public addresses. Pretty genius, right? Okay, so our little packet made it. It successfully navigated all the highways and byways of the internet, and it has arrived at the correct public IP address for the server. But its journey is not quite over. See, it's at the right building, but now it needs to find the right office or department inside. And that's where port numbers come in. If the IP address gets the packet to the right building, the server, then the port number gets it to the right apartment door, the specific app running on that server. It's exactly how one single server can run a website, an email service, and a file transfer service all at the same time. And a lot of these port numbers are standardized. We call them well-known ports. So, for example, if our packet is trying to load a regular web page, it knows to knock on port 80 for HTTP. If it's a secure encrypted page, it's going to head over to port 443 for HTTPS. This whole system is what lets your browser just automatically find the right application on the other end without you having to think about it. So, to recap, our packet is at the right address and it's knocking on the right door. Now what? Well, now it has to actually talk. And to do that, it needs to follow the rules of conversation. These rules, or protocols, are what makes sure the whole exchange of information is smooth and reliable. And it basically has two main choices. First, you've got TCP, the Transmission Control Protocol. Think of this as the super reliable messenger. It's like sending certified mail. It sets up a formal connection, it numbers every single packet to make sure they arrive in order, and if anything gets lost, it asks for it to be resent. Then you've got UDP, the User Datagram Protocol. This is the speedy messenger. It's like sending a postcard. It just sends the data and hopes for the best. It's all about speed over perfect reliability. So which one gets used? Well, the application itself gets to choose the right tool for the job. If you're loading a web page or sending an email, you need every single bit of data to be perfect, right? So TCP is the obvious choice. But what about a live Zoom call or an online game? A few dropped packets might just cause a tiny split-second glitch. That's way better than TCP pausing the entire stream to wait for a lost packet to be resent. In that case, speed is absolutely king, so you go with UDP.
Okay, so we've followed our packet all the way from your click, across the internet, to a server, and back. Let's just take a second to recap this wild journey and talk about why understanding it is so important. And this isn't just for network engineers, it's for anyone who's curious about how our digital world actually, works.
Because this knowledge isn't just some abstract theory. It's the foundation for real, practical network troubleshooting. I mean, the simple ping command, which you can run on your own computer right now, what does it do? It basically sends one of these little packets on a round trip just to see if a server is online and how long the journey takes. It's a miniature version of the exact process we just walked through. And if you're a professional in this space, this stuff is absolutely non-negotiable. I mean, if you work in cybersecurity or IT or you're a software developer, you have to know how data gets from point A to point B. It's just vital for building secure systems, for diagnosing problems, and for protecting networks from all sorts of threats. So there you have it, from a single click to a global journey and all the way back again, all happening in the blink of an eye. This hidden, super complex, but also kind of elegant process is what makes our entire connected world possible. It's happening right now, billions of times, all around us. So I guess the real question is, what part of this invisible world are you going to explore next?